G'day and welcome. Just a few days ago on my Facebook page I published a set of questions that were produced for some mathematics competitions, a bit like the International Olympiad on a smaller scale in my home country of Australia. And one of the questions was this one. If you were told that a squared plus b squared plus c squared was equal to ab plus bc plus ac, they wanted you to prove, I want to use this for working, I'll put down here prove that a equals b equals c, that the three letters must have the same value. Now, before you get totally turned off by algebra is a wonderfully symbolic way of thinking about amounts or values or relationships. And here we have particular relationships between numbers or values of some kind. The key to understanding this is actually the kind of algebra that you learn in around year 9, around 14, 15 years of age at school in Australia. And it's this theorem, that a minus b squared is a squared minus 2ab plus b squared. This is called a perfect square, where we have some expression multiplied by itself, and this is quite a common expression to learn. It's a very, very good pattern to learn. But I want you to notice that we have a squared plus b squared here, and on this side we have an ab, but we've only got one of them, and this has two. Well, let's see if this is of any use to us. I'm going to double everything here so I do get two ABs. So 2a squared and 2b squared and 2c squared makes two lots of AB and two lots of BC and two lots of AC. That's not difficult. So we've now got two of everything. If I bring this over to this side, and I want to use just one of the a squareds and one of the b squareds, this is what I get. I get a squared, one of those, so we're going to have another a squared somewhere else. Bring this over, and the b squared, I'm going to put parentheses around that. What's left? Well, we've still got that other a squared, remember? Hope you remember that. And I'm going to have to move the equal sign. I normally like them lining up for very important philosophical reasons, but we're not going to manage to do it. And remember, there was a b squared. So there are our two a squareds, there are our two b squareds. I'm going to write two c squareds down. So, and I'm going to put equals. So we're staying on the left-hand side of the equal sign. And you can see we've got our two a squareds, our two b squareds, and our two c squareds. And from this side, from the right-hand side of the equal sign, we're going to bring over the 2ab to here, minus 2ab. Bring over the 2bc and put it here. And bring the 2ac over to here. Oh, it's not plus. Minus. And now there's nothing left on this side because all those three have been taken away. So we've only really carried out two steps. We've doubled everything, and then we've brought these three terms here over to the left-hand side and done a little bit of rearranging. But notice what happens. This here is exactly what I discussed with you earlier. This is a minus b all squared. What's this? Well, it's the almost identical pattern, but instead of a and b, it's got a and c. This is a minus c all squared. And this one, same pattern again, but with b and c. This is b minus c all squared. Now this is considered quite a challenging question for school students, but I want you to see the logic of it. By doubling everything and bringing these bits over to make the centre of these patterns, because it was the centre of this pattern here, we've now got ourselves three perfect squares adding up to 0. Now, provided we're dealing with real numbers, that is numbers that are in the real world that you can measure, you cannot square a number that is multiplied by itself and end up with anything less than 0. 4 times 4 is 16, 5 times 5 is 25, minus 5 times minus 5 is also plus 25 because two negative numbers multiply to make it positive. So even if I choose a negative number and multiply it by itself, the square is going to be above 0. And that leads to a problem. If I have a square which is either equal to 0 or above 0, it certainly can't be negative. And I add it to another thing that can't be negative, and add it to another thing that can't be negative, the only possible way I can get 0 as a total is if this equals 0, and this equals 0, and that equals 0. Because if any of them aren't, my answer is going to be bigger than 0. Now, how do I get 0 with a minus b? When you're subtracting numbers to get 0, it means, therefore, that a must equal b. If I take a number away from itself, I just realise this looks a bit like an alien face. I've got a strange mind. But anyway, if I take a number away from itself, I get 0. This here means that a must equal c, and this here means that b must equal c. Therefore, if a equals b, and if b equals c, then a equals c as well, and there it is. We've just proven that a equals b equals c is the only possible outcome from that problem. This is not a standard question you would get in a school test. This involves a slightly higher abstraction of thinking. But I hope you've appreciated that there's a certain elegance, a certain niceness about it. Recognising this pattern in what you were given, being able to draw it out and understand how three things adding up to 0 when they can't be negative must all be 0. And that leads us to our conclusion. I hope you've enjoyed that. Just a little bit of an insight in some nice, very abstract algebra using quadratic equations, quadratic expansions. If you've enjoyed that, please click the like button and please leave a comment. I like getting feedback from you. And if you're not already a subscriber and would like to see more of this, then click on the subscribe button, and I hope you enjoy what you find in the next set of videos. Thank you for watching.